All right, let's get things started. Okay, hello everyone. Hope you're well. Good to see you again. I believe everyone is here. Good evening. So yeah, I guess we will get started. Let's actually share screen. Okay, so there we go. So hopefully, is there anyone here today who was not here in yesterday's class? Guess not. Okay, all right, good. So pretty much everyone showed up. Awesome. So if you haven't completed that questionnaire, I'm posting the link again in the chat right now so you can complete it. That was the one I gave at the end of yesterday's class. If you already did it, you don't have to do it again, but just for if you didn't do it. It's important for me to get demographics for the class, as well as I'm going to be using that cross-referenced with the Zoom login to take attendance, which is going to be important in a weekish or so. But yeah, other than that, we are going to jump in since it doesn't really seem like anyone's new. Everyone kind of knows what the deal is. Oh, the link is to a questionnaire. It's a Google form link that I just posted in the chat. It's a questionnaire that I asked you guys to fill out yesterday. Oh, I guess it didn't post to everyone. Okay, there it is. Okay. All right. If you filled it out yesterday, you don't have to do it again. But all right. As always, I'm going to turn off the video and we are going to let the math speak for itself. So yesterday we spoke about the class, the rules, we went over the syllabus, all that good stuff. And we actually started talking about chapter 7. Went over the logarithm defined as an integral. This is just a new way to look at the logarithm. It's a very abstract way of defining it. So we looked at that, and it turns out that you could derive everything from those rules that you should be familiar with. So we didn't really go too much more into that. I just mentioned some of the rules that I expected you guys to know. And we also spoke about the calculus of exponentials and logarithms, things that I expect you to remember. And we also now introduced the hyperbolic trig functions, which you may or may not have seen before. But again, these guys are just conveniences. There are times, most of the time, we can use trig functions in situations I'll be showing you. But every now and then, you are in a situation where a hyperbolic trig function might actually be convenient to use. And these are guys that are kind of like trig functions, except instead of using functions to track points on the unit circle, we track points on the unit hyperbola, which is why they're called hyperbolic trig functions. Anyway, these were their definitions. We looked over that and their graphs, and we defined all the other trig functions, the hyperbolic trig functions, which have very similar definitions. Now, the identities, the thing is the Pythagorean identity had a different sign, and so what happens is there are a lot of formulas in which they're almost like formulas that you would see in trigonometry, but they're just off by a sign here or there. And we looked at some of those, for example, the derivative rules. So all of these, the derivative of Cosh, Cinch, and Tanch, they're all positive, right? Which is a difference between the regular cosine and the hyperbolic cosine. The derivative of cosine of x is negative sine of x, but for the Cosh, it was positive. The derivatives of the hyperbolic secant, the hyperbolic cosecant, and the hyperbolic cotangent, those are all negatives, and these were the functions. The formulas I put you in boxes are the ones I'd expected to remember. We don't do a lot of work on cosecants and cotangents in calculus classes usually. And we could also talk about some other formulas in terms of the inverse functions. And these three are very convenient. Now, I didn't actually talk about where that formula actually came from. Maybe I want to describe one of those in a little bit. So let's, I don't know, let's do Cinch maybe, Cinch inverse. So, boom, boom, boom. The others are derived similarly. But let's figure out the derivative of the inverse cinch. So,
excuse me,
hello?
Professor.
Yes?
What topic are we dealing with today?
Today we're going to start integration, but we're finishing up hyperbolic trig functions. Why?
Oh,
What's
okay.
up?
No. I was just checking.
Okay. So we are going to figure out this guy. I just wanted you guys to see where these formulas kind of came from. There are a couple ways we can actually do this. And be sure to mute if you're not actually asking me a question. There are a couple of ways that we can do this, but one way, a nice way, is to say set y equals cinch inverse. And this means that the cinch of y would be x. This means that we can differentiate both sides implicitly with respect to x. So this is going to give us derivative of cinch is Cosh, and then we have to multiply by a y prime for the chain rule. And so you'd realize that your y prime is 1 over the Cosh of y. And we now remember that we had an identity earlier. We know that Cosh squared minus cinch squared was 1, which means you can solve for the Cosh. Now, technically it's plus or minus, but we know that the Cosh is going to take the positive sign because it's that guy that's above the horizontal. And so this would be 1 plus cinch. And so we can actually plug that in here. And so this is 1 over the square root of 1 plus cinch squared y. And cinch squared y, as we saw earlier, that was actually x. So this is 1 over the square root of 1 plus x squared. And that's how we found the derivative of this cinch inverse. And the other ones are derived very similarly. So you just, you can set this guy up, set y equals the inverse function, and then rewrite it without an inverse, implicitly differentiate, and then use your trig identities, the hyperbolic trig identities, to solve for one of these guys. And you can actually develop these formulas. So we have all these nice formulas right here. And you'll realize that there are situations in which they're almost very close to, I mentioned this earlier, but you can compare to the fact that we know that 1 over 1 plus x squared dx is equal to the regular tangent inverse of x plus c, right? So there's a difference in if we have a negative sign in the middle versus a positive sign in the middle. And just that one little sign change, it might make it convenient for you to use a hyperbolic trig function as opposed to a regular trig function. There are other ways to deal with this, but it's just something that you can know. It's very convenient to have sometimes. And so we can derive all these formulas. And I left you guys off with some examples that I wanted you to try for today. So we're going to do that and then put this topic to rest and actually move into what I consider is the actual real start of the course. The main goal is to start integration today. So we'll do that. But in the meantime, let's actually get these out of the way. Okay, so, and to answer the question in the chat, do you have to take the derivative of the angle inside the trig function too? Yes and no, it depends. If the chain rule applies, the chain rule always applies. So technically, if you were to do that, even when you don't have to, you don't just end up multiplying by 1. So, but in general, yes, if there's an inside function, you would need to take the derivative of the inside function as well. And maybe to answer, in answering that question, in going through these examples, you'll actually answer that question that was asked. Anyway, at this point, you guys had a whole day to think about it. So I'm going to turn over the class to you guys. You guys can help me get through these problems and then we can move on. So who tried this? Chime in, tell me what to do here. And let's get through this quickly. Go.
Well, basically what you would do is that, you would get 2x sinh x squared, Why? Because the
2x
chain rule
sinh
is,
of x squared?
involved. Yeah,
Because?
the chain rule is involved. Once
Right.
you do the chain, it wouldn't be product rule because it's only one trigonometric function. It's not like two involved. So or multiplied together. But because look, if you were to, take the
I got it. That's the answer. You've explained enough. So yes, that is correct. You know that the derivative of Cosh is sinh, and by the chain rule, you multiply by the 2x.
But it wouldn't be negative because this is the sinh and cosinh. It's all
right.
because
It's not negative, so you have to be careful with the formulas. So I gave you the formulas earlier here. So for the Cosh or the sinh, there are no negative signs. You have to be very careful. The negative signs are in weird places when compared to regular trig functions. So you have to be really careful with your signs here. But yeah, there are no negatives here. At least not for this formula. Derivative of Cosh is positive sinh. Okay. And that was that one. Maybe someone can help me with B. Someone else?
So for B, I got 2x times sinh x plus cosh x times, in parentheses, x squared minus 2. And to get that, you use the product rule. So
right.
from the problem you gave us, you have x squared minus 2 in parentheses as f or g, and then you have sinh of x as
right.
the other constant, and then you just multiply and then add.
Right. So you took f prime times g, and then here we took g times f g prime times f, or f times g prime, either way. But yeah, you would use the product rule here. Okay. So again, nothing too complicated here. I just want to remind you guys of rules that you should know already. Let's go into C. Do we have a volunteer to help with C? I keep writing it when I'm copying the. So as you see here, going back to the question that was in the chat, in this situation, you multiply by the derivative of the inside angle, whereas here you didn't really have to do that. Although technically if you did, you would just multiply by 1. So the chain rule always apply. You can literally always apply it. It's not going to cause too much trouble. You can get in trouble if you apply the product or the quotient rule too often when you shouldn't, in terms of algebra mistakes that could occur. But for the chain rule, you can just have it in mind that you're always applying it, and it's actually not going to be too inefficient. Right, how would we differentiate this?
Actually, you would have to take the derivative of, like, tanh, right? It would be
which is?
like, sec square of x over tanh of x, in a fraction.
Right, correct. And the rule that you're using here is what?
I would say, the taking the derivative of the ln, like,
Right, what's the
I
rule?
would say
Do you know the
The
rule?
chain rule.
So it's like d dx of ln of u
So
is
something to do with logarithms,
One
like
over u?
logarithms, like the u prime over the u.
right.
Simple.
That's what I wanted you to say. So that's the rule we're talking about,
Oh,
right? So where we see
so
the
you're
derivative of
actually
ln
like
of something,
You know
yeah,
what? Actually, I kind of got like misunderstood because I thought you were talking about the rule in like product rule or quotient rule. I thought you were asking for that type of rule.
yeah.
But if you were talking,
The rule being applied here is the chain rule combined with the log differentiation rule. But that's the rule that I want
but if
I
you were
want you
to
to have
ask
in
me
mind.
like the ln u, the derivative of it, what's the rule for that one? The formula would be u prime over u.
Yes. Okay. What about D? So this was the answer here. Box that. And the answer here, box that. Yeah, what about D? Who did that one?
Wouldn't D be a combination of the exponent of an exponent rule and a chain rule?
Which is?
So in terms of the exponent, you would
Yeah,
so
what's
you
the
would have
rule?
so it would be e to the sinh x times ln 5.
5 to the sinh x. Where did E come from? So the rule is if you want to differentiate a to the x, it's a to the x ln a, right? This is if your a is, right? And if you have, of course, if you have something instead of x, then you multiply by the derivative of that thing first by the chain rule. And so this is a chain rule version of the rule.
Professor,
Yes.
can't we also set it equal to y, and then we just ln both sides?
Yes, that's called log differentiation. That is a method that would work, but the difference here is that will be more inefficient because here, using the rules that I just wrote down, it's a one-liner, right? It's a one-liner here, as opposed to, or if you set y equals 5 to the sinh, then you can say log both sides. Then you would differentiate both sides implicitly, and that would be Cosh x times ln 5. Then you would multiply both sides by y. Which is the 5 to the sinh times the Cosh times the ln 5. And you can get to the answer that way. Correct. However, as you can see, to write that down as opposed to having this rule in your head, it's a one-liner if you have the rule in your head. If you go through the log differentiation way, you'll get to the answer, but it's just not very efficient. And in general, we would rather be more efficient than not. All right, how about E?
Hello?
Yes?
Hi, okay. So I used the quotient rule for this.
Okay.
And I got secant squared x times x minus tang x, and then all of that over x squared.
So it's tang x times a 1 technically over
Right,
x
yeah.
squared. Right. And this is by, of course, the quotient rule. We know that the derivative of f divided by g is f prime g minus fg prime all over g squared. And applying that rule, we get this. And I mean, nothing much to simplify here. I didn't give anything that's too crazy. So that's it. Yeah, just applying the quotient rule. Just want to remind you guys of the quotient rule. Let's do a couple integrals. Integral of tanh. Anyone? Integral of tanh?
Look, here's the thing, actually. I thought,
Yeah.
no one's going to speak out, but however, and you know what? Here's how you'd solve it. What
Okay.
you would do, actually, is the reverse of, like, of the reverse of tangent, right? More of the antiderivative rather than the derivative of it. But if you were to take a look at, negative ln of absolute value sec x, what you would do is that the derivative of sec x would be like, negative sec x tangent x over sec x. Therefore,
Okay.
the negatives cross cancel, the negatives, combine together, two negatives form a positive over, sec. And therefore, the sec x tangent x cross cancel with sec, and you get positive tang x.
Yes. So the answer is negative ln of the absolute value of
x plus c.
Secant hyperbolic.
Yeah, SECH.
Right.
Of x.
So I see that. Is that's the way you saw it first? Like you just noticed that formula?
Plus c. However, what you would actually like imagine is the reverse of the derivative. You have to.
Right. I get that's the strategy. Maybe give me another strategy. Can anyone come up with another one? That definitely does work, but I feel like most students wouldn't notice that.
I used a simpler one, so
Yeah.
I just used the identity of tanh. So cinch over Cosh, and then I didn't use sub for Cosh because the derivative would be cinch, and then you would solve the integral of 1 over u, which is a common integral. So then you have ln absolute value u plus c, and then you sub back in for u.
Right. And so I'm going to go with this method and write it down. Not that what Jason said was incorrect. It's perfectly fine what he said, if you guys were listening. However, I think the majority of students wouldn't really see that way. It's a little bit more nuanced approach. This is a more straightforward approach that I think most people would actually follow. So rewriting the tangent in the hyperbolic tangent as hyperbolic sines and cosines, and then doing a substitution is, I think, straightforward, and it's easier to follow for most people. So you'd have that, then the integral will become, of course, 1 over u du. And you would have, of course, this is equal to ln of the absolute value of u plus c, which is ln of cinch Cosh. And so that would be the answer. Now, if you are listening, it sounds like Jason's answer was different, but it's not. Note the earlier suggestion that the integral of tanh is the negative ln of hyperbolic secant is correct also. There are a couple ways you can do this. You can actually think about it the way that Jason thought about it, or you can just notice that minus ln of secant hyperbolic by the log rules, you can bring that -1 power up.
Before
And so that is just 1 over hyperbolic secant, which is just ln of cosine hyperbolic. So the log of the hyperbolic cosine is actually the same as the negative log of the hyperbolic secant. They're actually the same. So this also shows you one other way in which integrals can be different from derivatives, in that the answers can look quite different, even though they're all valid and they're all equivalent. You have to be a little bit more careful with your answers. So there are times when you guys could be practicing homework or practicing problems from the book, and you'll do a problem with a certain method and you'll get a certain answer. But then if you check the answer in the back of the book, or if you check Wolfram Alpha, or you check something else, the answer would look different to you. And whenever you're in that situation, I would say don't freak out. Just actually check whether the answers are equivalent. Check whether if you differentiate, however, for both, we can check by differentiating. And you'll notice that they'll both differentiate to give you tanh. Right? So we do have a couple options here. This is one way in which integrals are a little bit more complicated than derivatives. On top of that, as some of you already have seen, yeah, when it comes to computation, integrals are a lot harder than derivatives in general, because there are times when, even for very simple functions, we do not know how to integrate them. So let me just mention that. This is one, I don't want to say issue, but for lack of a better word, issue with integration. Answers may look very different, but can be correct. So there are many situations in which the answer, how it looks, can vary from problem to problem, and there's no unique way to represent the answer, but you should know how to check your work. Another issue is that there are simple looking functions. Let's that we cannot integrate, in the sense that we can't find a general antiderivative for them. Example, e to the x squared. This has no general antiderivative. So this is one of those scenarios in which the derivative of e to the x squared is trivial. The derivative of e to the anything is trivial. You just differentiate the power and multiply by the original function. The integral of e to anything, though, is not a trivial thing. You can, just by putting a square on the x, can go from a situation where it's super easy to integrate. So e to the x dx, super easy to integrate. In fact, you don't really do anything. You just add a plus c. Whereas e to the x squared dx, you now went from easy to impossible with the small stroke of a pen, right? So these are some things that you have to be wary of when you are studying Calc 2. Wait, I thought I saw, okay. When studying Calc 2. When it comes to integration, there are nuances and little pitfalls that you don't have to worry about with differentiation in general. So just be careful. And coincidentally, this example gave me an excuse to blabber on about that. But let's actually move on. Let's get through this with the last example.
Before we move on, actually, like for
Yes.
part F, actually, I thought how I actually solved this problem of the integral of tan x, you know, I actually, before I took any steps, I thought and imagined the derivative of tangent x and secant x and ln x, for example, part F of hyperbolic trig functions.
Yeah, I understand what you did. I know what method you did. I just, like I said, I don't think most students would see it that way.
I get your point. I saw.
So the way you did it is fine. There's nothing wrong with your method at all. I just, in terms of being able to actually write down a solution, like to write down what you did as a solution, I'd have to like write that down in English, you know, in paragraphs and explain what's going on, as opposed to writing it down like this. So this method it lends itself more to being able to be written down in shorthand form versus and being explained, and versus how most students would actually understand it or how they would see it first. But yeah, I get what you did, and there's nothing wrong with it. It's just a little bit ethereal. Okay, so how about the last one? Last example here. Can anyone do this one?
Actually, I thought and imagined this way. It's one, I learned this earlier from the internet. It's one, actually before I actually learned about this, before yesterday's lecture, I actually know that 1 over a, for any type of problem like this for integration, will be 1 over a tangent inverse, parentheses u over a. So what I actually thought is like, you know, you would involve the tangent inverse formula, you know, because you thought, no, that
For the tangent inverse
1
formula, you need a plus, not a minus. There's a minus here.
Because what I know is that 1 over 1 minus x squared would be the tangent inverse.
You mean tangent inverse,
Yeah,
the hyperbolic tangent.
Yeah.
Yeah. How do you apply that here?
Well, how I would actually apply it is that, you know, you see the e to the 2x. Whatever I found is that, you know, you would actually take the derivative of, like, you know, actually I don't think the derivative, but for a problem like this, you know, actually
okay. I don't know. Maybe you don't know how to explain. Does anyone know how to explain it? What they would do? Anyone else do this?
I haven't done this one, but I think just looking at it again, it looks like you might need to do some U subs.
Which is? What would you try?
I think the first U sub would be the 2x, since it's common in the numerator and denominator.
Okay, but if we did that, you would end up with 1/2 e to the u over 1 minus e to the 2u. Is that easier? Does that help?
Huh? Couldn't you do another U sub then? No. Where it would
Yeah, well,
be,
why would you do
I
2
guess,
U subs? You know what I mean? Like, it's inefficient. There's a way to do 1.
What?
There's a way to do 1. Like, you won't have to do a substitution and then do another substitution.
Damn.
Huh?
Could
Hello?
you do
Yeah,
it
not
with,
anymore.
Can you do it the same way that that she was mentioning with the U sub, but with 4x instead?
Our internet is bad.
Not still, yeah.
They call them in the what?
Doesn't
They do
go.
like those little tweaks and tweaks, and it just gets better
Hello?
from one day.
If you're not, please mute if you're not trying to participate.
What I actually
Okay.
picked earlier was u equals e to the 2x power. That's what I got
Yeah.
earlier.
That is, I think, the best option here, right? So again, go back to substitution back in Calc 1. Remember, the whole point of substitution is to do something, is to substitute an expression that, one, would make the integrand simpler in the sense that it would look like a basic rule. If I just replace the 2x or the 4x, things don't look much simpler than they do now. It's not really beneficial. You're going to end up having to do another substitution. It's not very efficient. However, notice that if you did the e to the 2x, your du is now going to be 2e to the 2x.
2e to the 2x power. And
so
actually,
you have your 1/2 du is equal to e to the 2x dx. And that's what you have here.
And if you were to imagine the arc tang,
Hold on. I'm speaking now. And this will give us 1/2 1 du over 1 minus, and the e to the 4x is actually e to the 2x squared, right? So if you note, e to the 4x is equal to e to the 2x squared. And so what you have here is 1 over 1 minus u squared. Now the goal of substitution is to, by the end of the substitution, you have a situation that is as simple as possible. Now, the most simple situation is a situation where you have a formula that tells you exactly what to do. And if you look earlier, we have a formula that looks just like that. 1 over 1 minus x squared. Now, over here, we have the 1 over 1 minus u squared. So that's a nicer substitution. If you were just to substitute the 2x or the 4x, we don't get to anything nice. You get to a situation where you still have stuff to do to it in order to make it very efficient. But at this point, that's just the inverse tang u plus c, which now you can replace the u.
The 2x power. And that's what I got. Plus c.
And so that's the answer.
Oh, okay.
Are you guys seeing what happened?
Yeah, it makes more sense.
Right. Now, so this is something that in Calc 1, when we were doing substitution, there were two main guidelines you were given about substitution in Calc 1. It turns out that one of them isn't very efficient for anything beyond Calc 1, and I'll talk about that later. One thing was you want to substitute an expression that makes the integrand complicated, so that once you replace it with a single variable, everything becomes easier. Easier means looks like a basic rule or looks like something that you can deal with a lot easier than the original. So that was always the first thing that you wanted to look for with a substitution. The second thing in Calc 1 was you wanted to find the derivative of that thing somewhere else in the function. And if you were off by a constant factor, it didn't matter too much. However, for Calc 2 and beyond, that requirement is not necessary. And I will show you examples later where that is the case. But those were the two main guidelines that you would have seen in Calculus 1. And so be careful with your substitutions, right? Substitution is a very powerful technique, but don't waste the substitution. U equals 2x is a waste. U equals 4x is a waste. You would end up having more stuff to do if you made those substitutions. You don't really get into an easier situation. Also, I forgot what I was going to say. But yeah, this is the way I would do it here, because look at that. We can get to a nice rule by going through that substitution. Okay. All right. So let's move on. So at this point, we spent a little bit more time than I wanted to spend on these, but it's good because now we're jogging our memory and all that good stuff. That's good. But yeah, those were the examples. Let's move on to integration, which is what I want to talk about today. Right. So we're going to start the integration phase of the class. And we're going to start to talk about fundamental techniques of integration. So I'm going to show you about 8 or 9 methods of integration here. Right, so we're going to spend a while in this section. This is chapter 8. which goes into integration, various types of integration, and various ways to approximate integrals when we don't know how to do them exactly. So that's what we're going to start. And let's actually take it a little bit back before moving forward. So in 8.1, 8.1 is stuff that you would have covered in Calc 1. So it's when you learned about what an integral was and how to integrate basic functions. And you learned about these basic rules here. So, which I expect everyone here to remember these. Now, things that you can ignore, rules that you can ignore, like this, you don't have to know. Like I'd never actually ask you about that, or this. Yeah, wouldn't really ask you about this either. Yeah, so here are some rules. Now, the formulas with the hyperbolics, you did not. So formulas 16, 17, 21, and 22, these guys are new. So you didn't learn about those in Calc 1, but as of now, you know those formulas. But yeah, everything else here you would have seen in Calc 1 at some point. Although we don't really emphasize the cosecants or the cotangents, right? But these are some basic forms that I do expect you to know. And you learned about that when you started doing integration in Calculus 1. So these are the basic formulas. Now, we also learned about substitution, which was another thing. And we also learned from substitution this little neat trick here. Basically, if you plug in a linear function, a substitution ends up dividing by that. So for example, so if you're off of one of these formulas by a little bit, and maybe instead of an x, you have a linear function, it's not too bad. What I mean by that is, for example, let's say we know that the sine of x, if we take the antiderivative of that, we would get negative cosine x plus c. So someone might ask, what is the integral of the sine of 5x? Now, a lot of students will actually go through and do a substitution here, u equals 5x and blah, blah, blah. It's often a waste of time because you should realize that the answer is just 1 over 5 cosine of 5x plus c. And that's because of the substitution would have divided by the constant. And this is true. This is true for sine of any linear function. So if it looks like ax plus b, as long as your a is not 0, the derivative is going to be minus 1 over a sine of a cosine of ax plus b. And so if instead of an x in your formula, you have a linear function, you just divide by the slope and then follow the formula otherwise. This is something that we learned from substitution, and it's just a shortcut. So for example, if you had e to the 7x plus 12, that's just 1 over 7 e to the 7x plus 12, right? So you don't need to actually go through a substitution. When you have a linear function, it is very straightforward. This is not true in general. You can't just divide by the derivative, but if your derivative is a constant, you can. Yeah, in terms of the rules that I expect you to, the basic rules I expect you to know from Calc 1 are these, but of course I expect you to know other rules that we will be learning. But yeah, so we learned about that. We also learned about substitution, and then we started building towards some computational strategy here. So back in Calc 1, you only really knew how to do 3 things. So either if you were faced with a random integral, right? How do you go about computing it? What you learned in Calc 1 was, well, step 1 is to try to apply a basic rule. Do one of these rules apply right away to the thing that you're looking at? If so, apply the rule and you're done, right? So that was step 1. Step 2, another situation that you could find yourself in is that a basic rule does not apply. However, you could simplify it to apply a basic rule. So, I don't know, for example, let's say we had x cubed plus 3x squared minus 7 all over x cubed, right? So you look at that guy, you see something like that. Doesn't look like a basic rule in your table. However, you'd realize that you could simplify this since there's a single guy in the denominator. You could actually divide everyone. In fact, you can simplify this a little further. So in other words, we could rewrite it so that basic rules applies. And right now, the power rule would apply to the 1. The power rule also applies to the minus 7x to the minus 3. And the log rule applies here. So this is x plus 3 ln of absolute value of x minus, well, you add 1 to the power and you divide by the new power. And so you can get that. Okay. Now, the third thing, if neither of those steps work, was to try a substitution. And remember, substitution there were special things you looked for to see if a substitution would work. What is an efficient thing to substitute, so on and so forth. I'm not going to go over substitution. If you want to review substitution, you can review it either from your notes or from the video lectures that I linked to you guys earlier. But yeah, as far as Calc 1 was concerned, when it came to computing integrals, these are the only 3 things you had to think about. Try to apply a basic rule. No, can't do that. Okay, try to simplify it to apply a basic rule. No, can't do that. Well, maybe a substitution is going to work, right? Now, in general, it turns out that these 3 things that you learned from Calculus 1 are actually things that you should always think about even beyond Calc 1. Whenever you are faced with a random integral, these are the first 3 things that I want to go through your mind. You're going to think about these 3 things first, always these 3 things first, always in this order, every single time. You see a random integral on a test, a quiz, anywhere in your homework, first thing you're going to look for, does a basic rule apply? Do one of these guys apply to what I'm looking at? If the answer is no, can I simplify it so that a basic rule will apply? If the answer is no, can a substitution work? And again, it's not always going to be super obvious when a substitution can work or not. However, if you're good with what a substitution is supposed to accomplish, you will know exactly what to try so that you don't waste any time. And you'll know whether a substitution would work just by kind of eyeballing it and see, well, if I were to do a substitution, this is what I would substitute and this is what would happen. And the more you do this, the better at it you get. And in theory, everyone here is pretty good at substitution at this point. But these are always the things that you thought about. So 8.1 is just going over some basic rules and substitution, which again, I expected you guys to know, but they are still relevant. These things are still relevant. They're still important. And I do want these to always be at the forefront of your mind. However, we are going to complete this picture. I am going to give you steps where you can do integrals where none of these methods would actually work for, right? So that's what I want to do for you guys today. This is, well, not today, we're not going to finish that today. But a huge chunk of this class is going to be just that. How do we compute random integrals? I give you a random integral, what do you do? How do you compute it? How do you calculate it? Hello? Hello? Is anyone talking? Again, please mute if you're not. Okay. All right. So let's continue. And all right. So when it comes to integration strategy, a big part of this course is just knowing how to do integrals, right? That's like a quarter of what this course is about, just knowing how to do integrals. And when it comes to that, strategy is going to be very important. As I was mentioning earlier, integration is not as straightforward as differentiation. So if you go down the wrong path, you could potentially end up in a lot of trouble. So in order to guide you through the right path or the safer path of actually getting through an integration problem, I'm going to give you a list of steps, which we are going to slowly add to this strategy. And then by the end, I don't know, 2.5 weeks from now or something like that, I can come back to this and I can summarize, okay, here's a general integration strategy for how to approach any integral in this class and many integrals beyond as well, okay? But again, these are always going to be the first 3 things you think about, always. It's always these 3. Now, the 4th thing I'm going to talk about is integration by parts. That is the main thing the main new thing I wanted to talk about today. And I just want to mention here is that these are always the first 3 things that you think about. However, beyond this point, the steps are in no particular order. So I know I'm going to teach you integration by parts as the next thing, but technically speaking, it's not always the 4th thing you think about. But integration by parts is going to be the next technique that I'm going to teach you. And after going through this, and when I give you guys a summary of the strategy, I'm going to tell you when you might try to use integration by parts, when would it be convenient, when you would try some other technique. But again, the first 3 steps are always the things that you think about first, all the time, every single time. Can a basic rule apply? Or can I simplify to apply a basic rule? Or will a substitution work? You always think these 3 things in this order every single time. Every time you see an integral, you think these 3 things. There's a reason I'm repeating myself so often. Hopefully by the 7th time I repeat myself, everyone will get it through their heads. Okay. Now, the 4th thing I'm going to teach you are, and the 4 here should probably be in quotations, because after the 3rd step, there's no real inherent order. It just depends on what you're looking at. Is integration by parts. Now, you might recall from Calc 1 that substitution is actually the reverse of the chain rule, right? That's what substitution is, right? If you differentiated something using the chain rule, substitution is how you would integrate that thing. Substitution was a method to reverse the chain rule. What integration by parts is a reverse of the product rule. Let me get a sip on some coffee here. Okay, so let's see where that would come from and how this method works and what it means. Suppose, recall the product rule. We even saw it earlier. We know that if we wanted to differentiate f times g, this is going to be f prime times g plus f times g prime. Now, what you can do here is you can integrate both sides. So let's say I integrate both sides. Okay. Now, we know from the fundamental theorem of calculus that the integral and the derivative will cancel each other out. Of course, there's going to be a plus c or whatever. But here, I'll just have f times g on this side. On this side, I will have the integral of f prime times g dx plus the integral of f times g prime dx. And what we can do is I can solve for one of these guys. I can solve for one of these integrals on the right side. So let's say I solve for the f times g prime. Then what this is going to look like, it's going to look like f times g minus the integral of f prime times g, right? Now, this is a very important formula. And here, what I'm going to do is I'm going to change the notation because traditionally there's a different notation. Set u equals the function f. Set v equals the function g. And so this means that your du is going to be the f prime of x dx. And your dv is going to be the g prime of x dx. And so this leads to the following formula. The integral of u dv is u times v minus the integral of v du. And this, ladies and gentlemen, is called the integration by parts formula. Now, why is it called integration by parts? Well, it turns out you think of these two guys as parts, right? You think of this as a part, and the g and the f are parts. So this is one part of the integral, the u is a part, and the dv is another part. So that's why they call it integration by parts. You break this thing up into parts, and you do it with one part at a time, is sort of the idea. That's where the name comes from. So this is called the integration by parts formula. And so the idea is I can compute the integral on the left by using this formula on the right. Now, of course, this is convenient in the scenario that this integral on the right is actually easier to compute than the integral on the left. If it's not, then integration by parts isn't going to work out for you. Now, let's actually do an example so that we can see this in action, and then we'll start to go over the nuances here and how to actually apply this. So let's look at x times e to the x. Now, what I want you to know is first, consider the first 3 steps in the strategy. Okay, so when you see integral of x e to the x, right? The first thing you're going to think, well, is there a basic rule for this? And if you look up in that chart that I gave you, or you just, well, really you should remember all those formulas, you'll realize that no, we don't have a basic rule for x e to the x. And then you might think now, well, can I simplify it so that it looks like a basic rule? And no, not really. What are you going to do to simplify x times e to the x? It doesn't really get much simpler than that. So now you're like, okay, can a substitution work? And the question would be, well, what would the substitution be? Well, since u equals x is always a bad substitution, probably u equals e to the x would be the substitution, but then the derivative is going to be 1 over x. You don't have 1 over x. It starts to get complicated. It gets more complicated in a hurry. So they won't work. But you should think about them. Right? So we considered them, and they're not actually going to work out. So now, what are we going to do? Well, there's only one other thing we know how to do. So what we're going to do now is try integration by parts. Now, the first thing you do when you're doing an integration by parts, we're going to do many more examples. So I'm going to walk you guys through this one, and then we are going to go through a bunch of other examples together. So the first thing you want to do is choose the parts. Notice here in the left of your formula, you have to know what is the u and what is the dv. So we're going to choose the parts. So here, what I'm going to do
Jhevon,
is that,
like, the
yes.
x for the u would be like, the x, and the dv would be like,
yes.
the e to the x power, or the v would be like e to the x, and and the du would just be like 1. And in order to solve this type of
dx, and Jason, I'm walking through this one. I will ask for your input later. Okay.
Yeah.
Okay. So I just want not to have different people chiming in when I'm teaching something brand new. Okay. So right now for the first one, I'm going to walk you through it. I'll get, trust me, like if you scroll down, you realize there are a lot more examples that we'll have to get through. So you guys will all get your shot at chiming in. Don't worry. For the first example, since it's potentially a brand new topic to some people, I want to go through slowly, just having one voice go through it. Okay. So the first thing you want to do is choose by parts. Choose the parts, right? So this comes down to choosing who is going to be u and who is going to be dv. And in this situation, I'm going to choose the x to be u, and the e to the x dx to be the dv. Now, once I chose my u, I can find the other parts. Choose the parts for the left of the formula. Second thing you're going to do is find the other parts. And probably I want these guys, because this is actually the problem being worked out. So the next thing you do is you're going to find the other parts. So this means you need to find what is du, the derivative of u. Well, the derivative of x is 1 dx. And you want to find the v. Well, the v is the integral of dv. The integral of e to the x is e to the x. Then the third thing you're going to do, plug into the formula. Right? So the formula is the integral of u dv is u times v minus the integral of v du. This is something, of course, that you have to memorize. And of course, I put it in a box because I want you to memorize. So this means that the integral of x e to the x is going to be u times v, right? So x was the u, e was the v, minus the integral of v du. So here, this is v, this is du. So in other words, this now becomes x e to the x minus the integral of e to the x. Right? And so now the original integral, the integral that we started with, notice that I can compute that integral by computing this expression. And lo and behold, the integral in that expression is a lot easier. In fact, once you do integration by parts, you get to the second integral. You're going to go through the strategy in your head all over again. Every single time you see an integral, you always go through that strategy. So you'll start with, okay, here's the new integral I have to deal with. Step one, is it a basic rule? The answer here is yes, it is a basic rule. So step one tells me how to deal with that integral. And so I just deal with it. Integral of e to the x is e to the x plus c. And that is going to be our answer. Okay. Now, before I move on and talk about this a little bit more, any questions on what I just did? Anything that I said so far that is confusing?
Oh, well, nothing is actually confusing. What I was trying to say earlier is that, speaking, actually not earlier, but right now, according to what you solved, another thing, what you can do to make it easier, you can just factor out the e to the x. You would get e to the x parentheses x minus 1 plus c, arbitrary constant.
Well, that's not easier. That's just a different way of writing it. I mean,
yeah,
that's factoring.
by factoring,
it's not
yeah.
necessary in this situation.
Well, that's
but
what I did.
Yeah, so but that would be the answer here.
Why can't we just factor it? Like, what's wrong with factoring?
So it's extra. You know what I mean?
Mm-hmm.
It's not necessary.
But if I got that as my answer, like, will I get the right answer though?
Yes, it would be marked correct because it's exactly the same thing.
Okay.
It's just like there's no reason to take the time to write down the extra line. You know what I mean?
Yeah,
like, if
the same time and energy.
It's exactly the same thing. So if you have you have a window in which you want to do like an entire test, you have a lot of problems to get through. You don't really want to waste your time writing down things that you don't need to write down. You know what I mean? So yeah.
Same time and energy.
Yeah. Now. Okay. So. Anyway, so all right. Now the question that Nohair, I hope I'm pronounced that right, asked is the question that I'm going to pose to you. How do you choose? So here, notice I chose u equals x and the dv equals e to the x, right? See right here, I knew someone would ask. So I'm going to ask this question. And how do you choose the parts, right? Here's something I want you to notice. Notice, if we chose differently, and this is very thick. Can I? Take it down a notch. I want you to notice what would have happened if we chose differently. Notice, if we chose differently, let's say I started out with u equals e to the x, and then my dv as x dx. Then my du would have been e to the x dx. Then my v would be x squared over 2. And then when I plug into this formula, I would get the integral of x e to the x dx equals u times v minus the integral of v du. And what you'll notice about this is that's more complicated, right? We just ended up in a worse situation by choosing in the other direction, right? So I started off with an x e to the x, and if I had chosen u to be e to the x and dv to be the x, I ended up in a worse situation, right? As opposed to choosing the u to be the x and the dv to be the e to the x, I ended up in a better, easier situation. So now the question is, how do we know what to choose? So clearly, this is the worst choice. Or let's say wrong choice, not the worst. I mean, there are a lot of bad choices out there, people. Now, the question is, the goal is you always want to make the choice in such a way that you do end up with a simpler integral. But saying that, and that's easier said than done until now, because I'm going to tell you how to do this. Here's how you choose, okay? And there are ways that you can reason through this and so on and so forth, but at the end of the day, this is just something that we figured out by trial and error. And so we use a mnemonic to help us choose. That's and some of you might know it already. What's the mnemonic? Does anyone know?
It would be like, normally the integration by parts, like,
Do you know the mnemonic? Listen to the question. The mnemonic. Do you know it?
The mnemonic.
No? Anyone?
The
Okay, so the mnemonic is called Liate.
like logarithm.
Right. So Liate stands for, the L in Liate stands for logarithm. The I in Liate stands for inverse
Trig.
functions. The A in Liate stands for algebraic, which is a misnomer. It doesn't actually make sense to say that in this context. What they really mean is polynomials.
And the T would be like trigonometric, and the
The
E would be like
T
exponential.
is trig function, and the E
Exponential.
are exponentials functions. And how you actually choose is, here's another example that we're getting into. And here's how we choose. The guys on the left get to be U first. And and the guys towards the right get to be u last. And so if you looked at x e to the x, you'll notice that the x is an a, while the e to the x is an e, and so the a gets to be u. And it turns out that if you follow this strategy, then if integration by parts can work out, following this order on how you choose things will get it to work out in the easiest possible way. So if you have x e to the x, again, this is a random integral you've never seen before. It shows up on a test or a quiz. The first thing that goes through your mind, is there a basic rule that I can apply here? If not, can I simplify to get a basic rule? If not, can a substitution work? If not, then you have a bunch of other options, one of which now is integration by parts. Once you choose that I'm going to do integration by parts, you now need to know how to choose the parts. How do you choose? Liate is how you choose. Whoever is the most to whatever kind of function is most to the left in this word gets to be the u. So for x e to the x would get to be the u. And as you see here, the proof is in the pudding. We actually ended up in a situation that we now know how to deal with.
Professor, I'm sorry, I got lost you. Can you please go over that again?
So liate is the mnemonic, right? L stands for logarithms, I stands for inverse trig functions, A stands for algebraic polynomials, T stands for trigonometry, and E stands for exponential functions. If you have a product of functions, like you want to choose the parts in an integration by parts, you're going to choose u based on the kinds of functions that appear. So here you'll notice that x is an algebraic, right? It's a. And the e is an exponential, right? A comes before e in liate, right? So the a would get to be chosen to be the u before the e gets to be chosen to be the u, right? And so if I have two kinds of functions being multiplied together, there are two different types of functions, then based on what kind of function they are, I can choose who gets to be the u based on liate. Does that clear up the confusion? Yes, liate is kind of like a PEMDAS, but for by parts, kinda. So hopefully that cleared it up. Okay. All right. So now let's actually try this. And maybe what I'd like to do is, I mean, I don't want to put anyone on the spot, but I think get to be u last means the order in which you would choose them to be u. Guys to the left get to be u's ahead of it. They're ahead in priority to guys on the right. You would choose the guys on the left to be u's first. Right? So it means if you have a log and an algebraic function, the log gets to be the u. If you have an inverse trig function and an exponential, the inverse trig function gets to be the u. If you have a log and a trig function, the log gets to be the u. Whoever's to the left is the u first. The other guy is the dv.
Sure. So on
Right.
if you're trying it a second time.
I know there are probably a few of you who have seen integration by parts before. So while I don't really want to put anyone on the spot, what I would rather do is someone who's kind of iffy on this, maybe to kind of give me suggestions on what they would do here. No wrong answers, just go and we'll figure out whether you told me the more efficient thing or not. Let's just actually work through this. Give me some suggestions, some ideas here. So we're gonna do this integral here. The integral of x squared times ln x.
Ln x gets to be u.
Ln x gets to be u. Now, again, I really want to drill this home, right? There's going to come a point where you're going to have to see a bunch of integrals, and there's not going to be any suggestion as to what to do first, what to do second. I'm teaching you integration by parts, so everyone knows to do integration by parts. But I really want you to get into the habit of going through the strategy. So when I see this integral, again, the first thing you think, Is there a basic rule that applies here? The second thing you would think, can I simplify it so that a basic rule can apply here? The third thing you would think, can a substitution work? And then you would worry about integration by parts or something else. Just so that's clear, I want to drill that home. It's a very important thing to get in your head. The first 3 steps in the strategy is always the first 3 steps, no matter what. Okay, so assuming we went through all that and we looked at, and we considered those 3 options, they didn't pan out. Now we get to integration by parts. And as was suggested, we would set the U to be ln. Why? Because now you'll notice that, hey, the ln, this part is an L, and the x squared, this part is an A. This guy gets to be U. Right? So you see this random integral. First thing goes through your mind, is this a basic rule? No. Second thing goes through your mind, can I simplify this to apply a basic rule? No. Third thing goes through your mind, can a substitution work? No. Fourth thing goes through your mind. Now, later on, you're going to have a bunch of techniques to choose from. However, at this point, the only other technique you know is integration by parts. So none of those pan out, so you know, okay, I'm going to do integration by parts. The next thing goes into your mind now is, I need to choose the parts. How do I choose? You choose by Liate. Look at the types of functions that occur, identify them as an L, an I, an A, a T, or an E, and then you choose U based on who is to the left in Liate. So in this case, L gets to be the U. The log gets to be the U. So here, U equals ln x, and my dv equals x squared. Okay, what is the next thing we do now? Oh, and there's a question in the comments. If 2 things are being multiplied in an integral, can we automatically assume it's integration by parts? The answer is no. For example, that is not something you do by integration by parts, right? That is something you do with a substitution. So again, this goes back to something I mentioned earlier, is that integration is a little bit more nuanced. It's not like with derivatives, where if you see a multiplication of functions, you can always assume the product rule is going to work. No such thing is true for integration. You can have a product of functions where integration by parts might not work. You might not need it, or something else might work. It's not as straightforward as differentiation. Okay, so now we find the other parts as was suggested. So du is equal to 1 over x dx. My v is equal to x cubed over 3. Then we plug into the formula. Let me call this I. It's going to be u times v minus the integral of v times du. So now what you see happens is that this guy simplifies, the x's cancel. And so now the original integral I can compute by doing this integral right here. So this is x cubed over 3 ln x minus 1/9 x cubed plus c. And there we go. That is the integral. And of course, you can differentiate this answer and check that you will actually get back the original guy. Questions on that? Yes, Kayla, go ahead. All right, I don't know. Are you typing? Okay, someone else? Question?
Wouldn't it actually the antiderivative of, 1 over 3 x squared, like, wouldn't that give you like, 1 over 6 x cube actually. Hold on a sec.
The antiderivative of x squared is x cubed over 3. And then you have the 1 over 3 times the x cubed over 3. So you get x cubed over 9.
Professor, I have a question.
Yes, go ahead.
When you do uv minus the integration of v dv, right?
V du, right. So this
V
is
du?
u times v minus the integral of v times du.
Okay, I got you. Thank you.
Yeah. So that's the formula that you have to memorize, which you probably haven't memorized it yet, but make sure you copied it down correctly from up here. So it's v du. I used to have a friend back in the day who he memorized it with by saying the word video very well. Video. I don't know. For some reason that worked for him. However you memorize it that way. But that's the formula. The pieces where they show up are very important. So u and dv are on this side, but v du is in the integral on that side. That's the formula.
Can you just scroll down?
Come again? Hello?
Can you just scroll down a little bit because I didn't finish copying.
To the final example?
Yeah.
Yeah. Someone else had a, video, it really stuck in your head.
Oh,
Yeah?
Professor, this is Kayla. My audio wasn't working. My
Okay.
question is, what happens if you have a problem and you know you need to do integration by parts, but both of the parts fit into the same letter of the mnemonic? So let's say both parts are inverse or both parts are trig functions.
We're going to look at examples like that later on.
Okay.
So yes, file that away. We're going to deal with that. In that situation, it turns out that it's kind of a free-for-all, but I'll give you guidelines on how to choose. So for example, there's an integral like the integral of secant cubed, which is such a situation. And the trick with that is to break it up into a secant and a secant squared and do integration by parts. And you're so Lyautey really only helps you when you have two different classes of functions. If you have two of the same kinds of functions, sometimes integration by parts will work, sometimes it won't. But that's a little bit more complicated. I need to teach you some more about integration before I can give you more guidelines down that road. But yeah, that is a concern. I'm glad that you're looking into it, but just file that away. We'll deal with that later.
Okay, got it.
Okay. Any other questions?
Actually, another thing you can actually do for x cubed over 3 ln x subtract 1 over 9 x cubed plus c. What you would actually do is that you would factor it. You would be like 1 over 3 x cubed parentheses ln x subtract 1 over 3 plus arbitrary constant c.
So if you were to factor this, you would actually factor out 1 over 9 x cubed. And again, that's completely unnecessary. There's no need to actually do that. Like the only time you would want to factor something is if you want to cancel something else. Like if you had a fraction, then I would say, oh, you should factor the top and the bottom to see if any common factors will cancel. But other than that, there's no real benefit to doing it. Like it's usually a waste of time. I mean, it's not wrong, but it's a waste of time. Like I wouldn't
why
care.
isn't when you factor, why isn't it actually x cubed over 3 parentheses ln x subtract 1 over 3 in parentheses plus arbitrary constant?
Well, this is a factoring question, but you always factor out the lowest power. That's a rule.
That's what it
so
is.
1 over 3 is 3 to the minus 1. 1 over 9 is 3 to the minus 2. You would factor out the 3 to the minus 2. That's just a basic rule of factoring. You always factor out the lowest power. So you would factor out the 1/9, not the 1/3, if you were factoring. Anyway, let's move on to another example. Let's do this. Suggestions.
We first check if it's applicable with basic functions, the first step.
Right. E to the x times sine of x. Do we have a basic rule for that? No, right? Can we simplify? No. Substitution? Like, what would you substitute? U equals e to the x, that's not going to help because you're going to get a 1 over x when you differentiate. U equals sine of x, that's not going to help. You're going to get a cosine of x when you differentiate. So yeah, the first 3 strategies out the door. So now we know, okay, integration by parts is what we're going to do. All right, what do we do?
Oh, hello.
Yeah?
Usually, answer.
Yeah? And what would that lead to here?
Would sin x be first?
So what are the parts here? We have an e to the x and we have a sine x.
Correct.
What are the parts here? What's the e to the x?
Exponential.
Right, so that's an e, and this guy is a t.
Trig. Yeah, trig.
Right. And so, by the way, you don't have to remember this if you don't want to. E and t are interchangeable in Leate. So it's kind of like how you have PEMDAS and then there's another thing called BODMAS that you probably, some people learn it, like, it depends, it's like a cultural thing. A lot of people in the Caribbean learn BODMAS instead of PEMDAS, and there are small nuances because sometimes things can be churned around in a rule. Another mnemonic is LIPIT. Mnemonic is LIPIT, which is the same thing, but it switches the E and the T. And this actually gives you the log inverse trig. P for polynomial, this one fixes that. This is an exponential, and this is a trig, where it switches the E and the T. The E and the T can be switched, so you do have some leeway there, but sure, let's follow Leate, let's follow the rules that we've been given. The T comes before the E, so let U be the sine function. And dV is the e to the x function. Du is going to be cosine of x dx, and the v is going to be e to the x. So this means that the integral of e to the x sine of x is equal to u times v. So that's e to the x sine of x minus the integral of v du. V du. So you have e to the x cosine of x dx. All right, so we end up with there. All right, so now to find that integral, we need to do this integral. How do we do that integral?
Are we going to make another substitution for?
Do by parts again?
Yes.
Yeah. So here, u equals cosine of x. The dv is equal to e to the x dx. The du is minus sine of x dx. The v is e to the x dx. All right. Let's go in and plug this in. Hopefully we get something nice now. Okay, e to the x sine of x minus,
because substitution doesn't work, right?
Right, yes.
Okay.
So yeah, in your head you would again go through, when you look at e to the x cosine of x, this new integral, you go through the strategy again. Every time you see a new integral, you go through the strategy. Is it a basic rule? Can I simplify it to be a basic rule? Would substitution work? All of those reasons, we shot them down pretty much for the same reason that we shot them down in the original. E to the x sine x and e to the x cosine x are very similar integrals, right? If the first 3 strategies didn't work on e to the x sine x, they're not going to work here. That being said, let's actually plug in the integration by parts formula. So this is u times v minus, and that becomes a plus because of the negative sign, the integral of v du. And that's this part right here. Okay, now what?
Do we plug in what we got into the integration of e to the x times sine x into the ex cosine x plus the integration of ex sine x?
How would we do that? Explain?
Oh, never mind.
Because now we have a new integral, right?
Yeah.
What do we do with this integral right here?
We do the same method again, integration by parts.
Hold on, it's the same. It's the same though, isn't it? Look at the original integral. Look at the original integral. And look what we just got. He showed up again. So what do you think is going to happen if we do integration by parts again? We're just going to end up with the same guy again, right? We'll end up in an infinite loop. And what do we do here? Well, there's nothing we can do. I guess we just go home. We broke math, I think. No. Some people have suggested it in the comment section. the chat window. I just used the comment section. Oh my God. Okay. Yeah. Now notice what you have. You have an equation where the thing you want to solve for is on two sides of the equation. How do you solve for that thing? Well, using algebra, right? You're just going to solve for the guy you want, right? In the sense that you're just going to distribute the signs. So just solve for the thing you want, right? We want the integral of e to the x sine x. So I'm going to expand the parentheses. And add it to both sides. Now, of course, there's a plus c here that we would get from the integration. Then I can divide both sides by a half. And that's your answer. So it turns out that this is a peculiar thing that happens with integration by parts sometimes. Sometimes you start out with integration by parts, but in going through it, you end up in a situation where, Christian, I don't know if he's impressed or he's like mind blown, I don't know. But sometimes you're doing integration by parts and the guy you started out with shows up again. This normally happens, yeah, it's wild. This normally happens when you have things that are they're very similar to their derivatives. So an exponential keeps looking like an exponential upon repeated differentiation. And a sine function or a cosine function, they'll keep looking like each other when you start differentiating. So anything where their derivatives kind of go in a loop, an integration by parts with those things is also going to go in a loop. But all you just need to do is you can break the loop by the moment you get the original guy. Just expand all parentheses and bring him to the other side. Then divide by whatever constant you need to, right? So that's how we would deal with that situation. So that's a very strange example, but it's a very important type of example, right? This is a revolving integration by parts. And that's that's not like an official name. That's just what I call them just because of habit. But yes, glad Kristen is impressed by that. That is one way to tackle this tough integral. Okay, let's do another one. X cubed e to the x. So what do you guys think? Right, x cubed is the u. Yeah. So you realize that here, x cubed, and again, you go through this strategy in your head. Is there a basic rule? Can I simplify to look like a basic rule? Can a substitution work? You realize that none of those options would be very viable here. However, your x cubed is an a, and your e to the x is an e. And so u equals x cubed, dv equals e to the x dx. So this means that the integral this means that your du is equal to 3x squared dx, and your v is equal to e to the x. This means that the integral of x cubed e to the x dx is going to be u times v minus the integral of v du. So now we have to do this integral. You'll notice that that is, again, something you would want to do by parts. So you go x cubed e to the x minus, maybe I should. We're learning for the first time, so I should start writing everything out. Okay, so again, I would do integration by parts over here. U equals x squared, du is equal to 2x, dv is equal to e to the x, v is equal to e to the x. So now this is going to become x cubed e to the x minus 3 times u times v minus the integral of v du. And now you'll realize we have another integral. How do we do that integral? Well, we go through the strategy again. Is it a basic rule? No. Can I simplify to do a basic rule? No. Can substitution work? No. Integration by parts. All right. So we're going to do that again. U equals x. This is actually the first example we did. So my du is equal to dx. My v is equal to e to the x. And now I'm going to plug that in. So here I have x cubed e to the x minus 3 times x squared e to the x minus 2 times u times v minus the integral of v du. And at this point, we end up with something that we know how to integrate very easily, integral of e to the x. So we'd end up with x cubed e to the x, parentheses are very important here, you're gonna have to watch the signs, minus 3x squared e to the x plus 6x e to the x. Right, and now the integral of e to the x is of course e to the x. You multiply that by 2, you get positive 2 e to the x. So now you get minus 6 e to the x plus c. Whew. And so this one, we had to do integration by parts. We had to go through that like 3 times. 1, 2, 3, right? With an x cubed. So the idea here is we had to take the algorithmic approach. We just broke it down power by power, broke it down from an x cubed to an x squared, then go from an x squared to an x. Then finally we can get to something that's doable. So this is another scenario that you can find yourself in. Just doing repeated integration by parts, you just keep going until you break something down and get it simpler, right? So there are some integration by parts examples that are straightforward. You do integration by parts once and you get something nice. Sometimes it revolves on itself. So you'll get something back that you already started with. But of course, how you deal with that is you just, you expand parentheses, bring the thing you want to solve for to one side. This one, you'll realize, is a different kind of scenario. You have to keep doing integration by parts, but eventually you break it down to some indivisible part that you can just actually get to an answer right away. You can get to it a lot quicker. Yeah. So how many times would we have to repeat integration? As many as you need. To answer that question, maybe I should ask you another thing that I would expect you to be able to do. Ta-da! So what are we going to do here? X to the 5th e to the x. Hopefully that's starting to answer Marilyn's question. So, of course, here, what's going to happen, right? We have an x to the 5th. So, all right. Kayla just stole my thunder. So, okay, because I totally agree with that, right? So here's what I would do. I would look at this and I would be like, does a basic rule apply? No. Can I simplify to apply a basic rule? No. Can I do a substitution? No. All right, the only other thing I know is integration by parts. Do I want to do integration by parts? Hell no.
No,
nah.
actually, like, Jhevon,
Yes.
in order to solve this type of problem, what's an easier way to solve this problem in case when you try to solve integration by parts, especially for a particular problem like this, what's the easier way? The tabular method. The tabular method.
Really? Wow. How did you know? Yes, it turns out there is a better way.
Yeah, the tabular method, it absolutely works. If you try that problem, I
right.
swear to
So
God,
the thing is, most people here don't know the tabular method. That's actually something that we're going to do in the next class. So no, I do not expect anyone here to actually do integration by parts 5 times in a row. That is just overkill. Even 2 times in a row is kind of pushing it, but that's kind of fine. But to do it 5 times in a row, nah, I would not do it. I would go with Kayla's answer and choose, I am not doing this. There is a nicer way, there is a better way, and as you heard Jason say, it is called tabular integration, which I do have over here. Now, of course, we are, I believe, pretty much out of time. So I'm not going to go into that, but yeah, I will show you tabular integration next time. So it's called tabular integration. So this is a way to streamline integrated by parts. Especially when I have to move the chat box out of the way here. Especially when you have to do it repeatedly, right? As you can see here, just doing it 3 times in a row was already kind of annoying, or people be like, oh, it's longer than my English paper or whatever. Very funny. Wait until you go to differential equations, then you'll see what a long answer looks like. But yeah, even doing it 3 times is annoying. Can you imagine how many nested parentheses we'd have to go through doing it 5 times in a row? There has to be a better way. There is, and that's what we're going to start next class with. I'm going to teach you a variation on integration by parts, which is called tabular method. And I guess Jason can help us get through that one.
So if you were to determine the final answer, you would actually get x to the 5th power times e to the x.
No, don't spoil it. Don't spoil it. We're going to do this tomorrow.
Sorry.
We're going to do this tomorrow.
I apologize.
What I would say, I would probably leave some of these examples. These are some examples we're going to redo with the tabular method, so I can show you. But what you can probably start doing at this point is start attacking these more examples. Yes, so be careful not to spoil the surprise, Jason. We will do this tomorrow. I will leave these guys for you to do, but I will also teach you tabular integration tomorrow. But I like you guys to start thinking about this one. So I will leave these examples here. for you guys to do with integration by parts. You can do regular integration by parts. Try these for tomorrow. And we will go through them as well as tabular integration. So there's some things I want you guys to practice for tomorrow's class. We are going to go through them together, but I would like you guys to actually attempt them. Just as many of you did today. Very happy you guys did it. And I'm going to show you a way that you can get through this very quick. It's going to be amazing. I'm going to teach you that method, and you're actually going to be able to do an integral like this very quickly. So by not paying attention, you want to do integration by parts 5 times, you will take forever, almost as long as it would take to factor your answer unnecessarily. Then, yeah, that's just a joke. Okay, then we'll actually go through all of these together. But these are some examples that I want you guys to try on your own for tomorrow's class. You can do all of them with integration by parts without doing it too often. So you don't need many repeated integration by parts here. But actually take a shot at these. We'll pick up with those tomorrow. And again, when I post the video, I'll post a PDF of this at some point tonight, and you guys can start getting to work on that. But in the meantime, right now, just like take a screenshot or something. And we'll pick up with those tomorrow. And once we finish these examples, we'll end this section. Yeah, once we finish with these examples, we'll end this section and move on to more integration techniques. All right, thank you. I'm glad you understood. Any questions, let me know. Otherwise, stay safe, everybody, with all the craziness that's going on out there. Be careful. I know a couple students have reached out to me. They're in neighborhoods that were affected by the protests and all that sort of stuff. So I know it's a really tough time for some people out there. However, reach out to me if you have any issues with anything. Set up a meeting and we'll discuss what we can do moving forward. Yeah, curfew starts, so you guys better be home. All right, we'll stop. We will stop there. So that ends today's class. Try those examples. I will see you guys in the next one. Take care and bye, everybody. All right.